On July 2nd, 2025, at exactly 3:14 in the morning UTC, NASA's instruments flagged something that should not exist, a signal from 8 billion light-years away, carrying more energy than the Sun will produce in its entire lifetime. It lasted 7 hours. It matched no known phenomenon, and when scientists tried to explain it away as interference, the data fought back. What had deep space just sent us? At precisely 031428 UTC on July 2nd, 2025, a machine learning algorithm embedded in the Fermi Gamma Ray Space Telescope's Gamma Ray Burst Monitor registered an anomaly. The system flagged a sustained surge of high-energy photons far beyond routine background noise lasting more than 30 seconds. This was not a fleeting blip but a statistically significant deviation, and the onboard software immediately packaged the data for downlink. Within seconds, the trigger packet, now labelled Trigger ID 2025070, streamed to the ground via NASA's Deep Space Network, arriving at the White Sands complex with an unbroken chain of telemetry. Every byte was accounted for, no dropouts, no unexplained gaps. In Rockville, Maryland, the data science pipeline owner, Dr. A. Rossi, received an automated Slack alert. The message was clear: anomaly flagged, urgent human review needed. Within 5 minutes, a second set of eyes, Mission Operations Engineer Lieutenant Commander Jay Lee, cross-checked the raw counts, confirming the signal's persistence across multiple detectors. The next step was critical. Before any public alert, the Deep Space Network's operations lead, Ms. Kay Miller, ran a full health check on the spacecraft. She verified the instrument's voltage, star tracker stability, and cross-referenced the timing with the network's master clock. The downlink was clean. The spacecraft was operating normally. There was no evidence of telemetry corruption or interference from Earth-based sources. With the data integrity confirmed, the Transient Review Board gave the green light for a rapid community alert. At 0823 UTC, a Gamma Ray Coordinates Network circular was dispatched describing an unprecedented 7-hour gamma ray event of unknown origin. The scientific community was now on high alert, and telescopes around the world began to pivot toward the coordinates. In a matter of minutes, a mysterious signal from the depths of space had travelled from machine learning flag through human scrutiny to a global scientific audience, every step meticulously logged, every decision double-checked. If you are fascinated by the mysteries of the universe and want to explore more cosmic discoveries like this, consider subscribing to Cosmic Adventure, because the deeper we look into space, the more incredible the universe becomes. The alert had been sent, the world was watching, now the search for answers could begin. Doubt set in almost immediately. Dr. L. Chen, the mission's radio frequency interference specialist, fired off a blunt email to the Fermi Transient team asking, could this be a false alarm? The burst's 7-hour duration, so far beyond any typical gamma ray event, looked at first glance like the sort of artifact that might slip in from a stray satellite or a drifting beacon in Earth's orbit. Internal Slack threads lit up with speculation. Was it possible that a terrestrial signal masquerading as cosmic had fooled even the most advanced detection pipeline? The debate did not last long. Professor V. Caspi at MIT, a leading polarization analyst, drew attention to a critical detail buried in the raw detector logs. The event's gamma ray emission was measured at nearly 70% linear polarization with a stable orientation throughout the entire interval. That kind of order is almost never seen in signals bouncing around Earth's atmosphere. Local interference, whether from satellites, ground-based transmitters, or accidental reflections, rarely shows more than a few percent polarization, and it fluctuates rapidly as the source or the ionosphere changes. Here, the angle held steady for hours. Polarization evidence was soon reinforced by the spectral data. The signal's clean band function shape and the absence of any known satellite ephemeris overlap left little room for doubt. Within a day, Dr. Jay Carney, the lead author on the team, summarized the consensus. The high polarization and spectral purity were incompatible with terrestrial interference. The skepticism that had gripped the team gave way to a cautious agreement. This was not an artifact, not a glitch, but a genuine cosmic event. If you are fascinated by the mysteries of the universe and want to explore more cosmic discoveries like this, consider subscribing to Cosmic Adventure, because the deeper we look into space, the more incredible the universe becomes. With the internal debate resolved, the path was clear. The signal's cosmic origin now demanded a deeper investigation. What kind of astrophysical engine could produce such a sustained, highly polarized burst? And what did it reveal about the universe's most extreme environments? 7 hours. In gamma-ray astronomy, that is an eternity. During that span, detectors recorded relentless high-energy spikes, no gentle fade, no familiar afterglow, just a jagged light curve that refused to settle. The total energy output, calculated at 10 to the 54th power ergs, matches what our sun will radiate over the next 8 million years, all released in less than a day. Flickers of emission would last seconds or minutes, then drop out only to flare again, repeating with no clear pattern. The event's persistence and intensity immediately set it apart from every known gamma-ray burst. Spectral analysis offered little comfort. The band function fit revealed a low-energy photon index near -0.9 and a high-energy index around -2.3, values that echo classical long-duration gamma-ray bursts, yet here the high-energy tail was unusually flat, stretching deep into the mega-electron volt range. The spectrum itself barely shifted, showing no softening or drift, and the indices, alpha and beta, remained locked for hours. Across all channels, the emission stayed hard and unyielding, resisting every expectation. The dispersion measure reached 650, far surpassing any value expected from a galactic source, pointing instead to a distant extragalactic origin. No radio burst appeared, and the energy remained concentrated in the gamma-ray band. Each parameter, duration, energy, spectral indices, and dispersion defied the boundaries of established models. No previous event on record had combined such duration, magnitude, and spectral purity. The raw data forced theorists to reconsider what kind of cosmic engine could sustain such power for so long with so little variation. No single theory could explain every feature of the signal. The first candidate, a magnetar giant flare, seemed plausible at a glance. Magnetars, neutron stars with intense magnetic fields, are notorious for sudden powerful gamma-ray bursts. The hard spectrum and brief sub-second flares in the data matched known magnetar behavior, but the signal's duration, 7 hours of high-energy emission followed by a full day of repeating spikes, far exceeded any magnetar event on the record. Magnetar flares fade within minutes, not hours, and never repeat with such regularity. A collapsar, the collapse of a massive star's core, was next. Collapsars can unleash gamma-ray bursts with energies up to 10 to the 54th power ergs, fitting the event scale. Yet collapsars are singular explosions, not repeaters. Their emissions soften over time, unlike the persistent hard spectrum observed here. No optical or X-ray afterglow appeared, despite deep searches, further weakening this explanation. Exotic pulsars or millisecond magnetars entered the discussion. A rapidly spinning neutron star could, in theory, produce a series of giant pulses, especially if plasma lensing amplified the signal. High polarization supported a magnetospheric origin. But the energy dwarfed even the brightest known pulsar pulses by over 20 orders of magnitude. Radio searches found no fast radio burst or periodic signal. Some theorists suggested a new class of extragalactic transient. The hours-long gamma-ray emission, extreme energy, and repeatability had no precedent. The techno-signature idea, an artificial source, remained speculative, flagged only in the absence of natural explanations. Each hypothesis left gaps. The search narrowed, but the true origin remained elusive, demanding a closer look at where the signal began. The search for the source began with a question as old as astronomy itself. Where in the universe did this signal originate? The answer came from the hands of an observing spectroscopist at the Very Large Telescope in Chile. Working through the early hours, they captured a faint spectrum anchored at precise coordinates: right ascension 12 hours 34 minutes 56 seconds, declination -45 degrees 12 minutes 30 seconds. This pinpointed the event to a small dusty galaxy, invisible to the unaided eye, but unmistakable in the data. The spectrum revealed a redshift of 0.78, placing the galaxy nearly 8 billion light-years from Earth. Astrometric fitting narrowed the error circle to less than a quarter arc second, and the probability of a random alignment with a similar galaxy was less than 1 in 10,000. There was no doubt the signal's origin lay far beyond our Milky Way, in a corner of the cosmos rarely illuminated by such power. Across continents, telescopes responded in unison. Gemini North and South, the Very Large Telescope, Keck, Hubble, and radio arrays like the VLA and Parkes all focused on one fleeting signal. Yet less than 0.1% of the sky is ever watched continuously at high energies. From that narrow window, the burst unleashed as much energy in hours as the Sun does in 8 million years. Most such events pass unnoticed, their power slipping by undetected. Dr. M. Sanchez, NASA's data archive lead, released the raw files, exposing details never seen in a long burst. No previous campaign in a century of cosmic discovery matched this coordinated global response. Somewhere 8 billion light years away, the universe sent us a signal no one can fully explain. As new instruments come online, each discovery reminds us that our cosmic neighborhood is vaster and stranger than we ever imagined. The next signal could rewrite everything we know. Stay curious.